My name is John O'Reilly. I'm based in Galway in the west of Ireland. I work remotely for a Norwegian company called Neat, and it's an absolute pleasure to be here in Copenhagen at KotlinConf today. The plan today is we're going to go on a guided tour of various libraries used in a number of the Kotlin Multiplatform samples I've been working on, along with other folks over the last 5 years or so. Going to just start with the usual show of hands. How many people here have used Kotlin Multiplatform? Oh, wow, okay, quite a few. And how about Compose UI Multiplatform? Okay, big enough number, and obviously not the same as KMP. And as you can imagine, I've been asking this question at least about KMP in talks over the last 5 years, and it's been fantastic to see the steady increase in people using it. Just to start with a tiny bit of background, I started taking an interest in Kotlin Multiplatform around the end of 2018. And I had at this point here just about got something basic up and running using this Galway bus project. This had just been an Android app at the time, and was in general a project I was using to try out new technology. Interestingly enough, the following day, June the 3rd, 2019, SwiftUI was announced at WWDC and was available to try out straight away, which of course I did. Jetpack Compose had been announced at Google I/O a few weeks before that, and so began this amazing combination of declarative UI and Kotlin Multiplatform. And 5 years later, this is where I find myself with 11 KMP samples now, and a number of them created in collaboration with other folks. So these samples cover use of a range of different architectures, remote access, persistence approaches, etc., and different libraries used for each of those in many cases. Not going to go through all of them, but we'll use a number of the samples to illustrate various patterns and some examples of how those libraries are used. By the way, I'm including links in various places so that hopefully these slides can act as somewhat of a reference for folks that want to look into them in more detail at a later point. And we're going to use these specific 5 samples as a basis for our exploration, illustrating use of the KMP and CMP libraries shown. These cover different approaches for retrieving data from a backend, persisting locally, dependency injection, ViewModel component sharing, Swift Kotlin interop, packaging, and also include a number of Compose Multiplatform UI libraries as well. There's quite a few libraries here, so obviously we won't be going into great detail on each one, but hopefully we'll provide at least a flavor of what the library does and how it can be used. Before we get into details, I just wanted to give a big shout out to all the folks who've contributed to this samples over the years. In a number of cases, this was their first open source contribution. And conveniently, I had a contribution this week to allow a nice even layout like this, which was nice. Thanks, by the way, to Stylianos Gakis here for the Kotlin script to query GitHub to get this information, which I then, of course, felt compelled to put a small Compose for Desktop app around, as you do. By the way, these are the full set of libraries used in the samples I have. We have a number of the standard JetBrains libraries, a couple of libraries from Google that now support KMP, and then various third-party ones. Important to mention, of course, that there's a ton of other libraries available now as well. And speaking of which, just to highlight how many KMP libraries there are available these days. When I started looking into KMP around the end of 2018, I think there was maybe a handful available at the time. And not only do we have third-party libraries, but likes of Google now porting many of their libraries to work with KMP as well. So the first of the 5 samples we're going to cover is people in space. This was the first dedicated Kotlin Multiplatform sample I created. The functionality in it is quite minimal, shows the list of people in space and the position of the International Space Station. But it covers a wide range of platforms. We have Android, Wear OS, and iOS here, along with Compose for Desktop, and WASM-based Compose for web clients. It also has a watchOS and a macOS client, along with a Ktor-based backend. And this is a high-level architecture diagram showing the key moving parts of the project. In this sample, we're using native view models, but in most of the others, they're shared. I wanted in general to ensure the samples collectively covered a range of different usage patterns. The project was initially intended to be as minimal as possible, so basically just repository and remote API classes in the shared KMP code. We're using Ktor to make HTTP requests to the backend, and SQLDelight then to store the data retrieved in a local database. And that database is what's used then to drive the UI. And in this section, we're going to talk about Coin, Ktor, SQLDelight, and KMP-NativeCoroutines. First library we're going to talk about is Coin. It's a dependency injection framework I use in most of the KMP samples I have, and one I've been using in work projects as well for several years. I think it's also probably fair to say that it's currently the most popular DI library used in KMP projects. It's probably a good point to ask, how many people here are using Koin? Okay, quite a few. As I said, I think if you're working in KMP, it's probably more than likely the one you're using. There's a few others around, and there's a few others I think that are emerging, but certainly the most popular one right now. We define our dependencies in a series of Koin modules. In a KMP project, we typically have one module for common dependencies, as shown here, and then use KMP's expect actual for a module that we define for each platform, as we'll see shortly. I'm also showing here an example of injecting the people in space API dependency into the repository class. In this project, we're instantiating that repository class directly from Swift. So using Koin component, which allows us to inject dependencies as using the approach shown here. In a project where a view model, for example, is shared, then that repository instance would typically be injected into the constructor of the view model, and we wouldn't need to use Koin component for this class. And these are the platform modules for iOS and Android, for example, using for the SQLDelight database driver and the Ktor HTTP client engine, which need to be defined separately for each platform. And as we'll see shortly, these platform-specific versions of these dependencies will get injected in automatically to common code that depends on them. Next up, we're using Ktor for making remote HTTP API requests to the backend. Ktor includes libraries for both client and server, but we'll be focusing on the client here. By the way, there are Ktor-based backends in a number of the samples if folks are interested in taking a look. And this is some of the plumbing we create to allow using Ktor. We're using the Kotlin X serialization library, so just need to configure that so it can be used, for example, for deserializing the JSON we get back into Kotlin data classes. That JSON instance is passed to the create HTTP client method that's shown here, along with the client engine we showed earlier. Note again, this is common code, but then appropriate platform-specific versions of that engine will get injected. Here we see again the Android and iOS specific versions of the Ktor engine being created in Koin platform-specific modules. Next, we're showing the data classes for the list of people and also for the position of the International Space Station. The JSON return from the backend will automatically be deserialized into those classes by the Kotlin X serialization library. And then two methods, fetch people and fetch ISS position in the API class that use Ktor to make requests to the backend. And again, we use Koin here to inject the HTTP client object into the people in space API class. Okay, now that we've got our data from the backend, we need to store it locally. And for that, we're using the SQLDelight library. This works by generating type-safe Kotlin code from a series of SQL statements. And these are the SQL statements for the people in space sample. We have a statement for creating the table, and then ones for inserting, selecting, and deleting data. And note that the names shown above the statements are what are used in the Kotlin code generated, as we'll see next. We can now use that generated code to store the data we got back from the backend into a local database. We create a transaction here, and within that, in this example, we delete existing entries and store the new ones. Again, note that delete all and insert item were generated based on what we defined in our SQL file. And here we use the generated code to retrieve data from the database and expose as a Kotlin flow, which we will use to drive our UI. And we also use this mapper here to convert the result of the query into a Kotlin data class. Also, just a very small example of how, from the project of a SQLDelight migration, database migration as well. As an aside, the endpoint I used to get the data doesn't include this info. So I ended up creating a Ktor-based backend that proxies the request and augments a result with that additional data. So I had to add that to the database as well. And that backend, by the way, is in the repo if folks are interested in taking a look at some point. One other library I want to highlight for this sample is KMP Native Cortines. It supports mapping Kotlin coroutines to a range of different Swift concurrency frameworks. But these days, I'm using it primarily for mapping to the new structured concurrency capabilities introduced in Swift 5.5. Showing an example here from People in Space, where we have a Kotlin method in shared code that returns a flow representing the position of the International Space Station. And then in Swift, we use for_await to observe the data. For_await being effectively equivalent to collect in Kotlin. And note that if this is cancelled in Swift, then that cancellation gets propagated to the Kotlin flow as well. We can also use KMP-NativeCoroutines to seamlessly invoke Kotlin suspend functions using Swift's await. An example we're using is confetti. This is a Kotlin Multiplatform project for showing information for a range of conferences. For example, KotlinConf. It includes various clients along with the GraphQL backend, thanks to Martin Bonan here from the Apollo Kotlin team. He will be here, I'm sure, to answer any questions people have. Here we have the iOS and Android clients, and also a Wear OS one, which was created by Yuri Shrimka, who's also here, who, by the way, has also contributed Wear OS clients to a number of the other samples as well. So thank you, Yuri. It also has a Compose for Desktop client, and also working on a WASM-based Compose for Web one, as shown here. Again, showing the high-level architecture. Key thing here is the use of Decompose components, and using Apollo to interact with the GraphQL backend. We'll talk about both shortly. By the way, just another quick show of hands. How many people here are using GraphQL? Okay, definitely Martin, anyway. And people using GraphQL, how many people are using Apollo? I guess it's, you can raise your hand, Martin, as well, please. Yeah, yeah. So I believe it's certainly the most popular client library for accessing GraphQL. It's great to see. That's the other thing that I've seen steadily increasing, is the popularity of GraphQL, which is good to see. By the way, we're also sharing some of the Compose code across the clients, including on iOS. And showing examples in this section of Apollo Kotlin, Decompose, Multiplatform Settings, and Coil. As mentioned, the clients in this project interact with a GraphQL backend, and for that we're using the Apollo client library. As described, it's described as a strongly typed caching client, and that automatically generates APIs from your GraphQL queries and backend schema. The caching aspect of this is very important as well, giving us effectively an all-in-one solution for both retrieving the data from the backend and storing it locally. We need to create an Apollo client object to make various requests, and this is an example of how that can be done. We provide, in this case, the URL, a header containing the conference name, and details about the in-memory and persistent cache we'll be using. And showing a few examples of its usage. Firstly, for retrieving the list of conferences. Shown here is the GraphQL query that this is based on. And then use of the Kotlin code that Apollo generated to execute that query. The conference data class referenced here is also generated by Apollo based on what we specified in the query. And then this is what's known as a GraphQL mutation, where we update data in the backend, in this case adding a bookmark for a session. And again, we make use of the Apollo-generated code to perform that mutation. Next up is Decompose. This is a library based on the idea of breaking your code into a tree of lifecycle-aware components that contain observable state, have routing navigation functionality, and into which you can plug your UI. So this library is broader in scope than most of the libraries we're showing in the talk, and quite a few moving parts, but hopefully these will become clear in the following slides. Here are most of the Decompose components in the Confetti project, for example. We see, for example, ones for the list of conferences, session info for a particular conference, speakers, bookmarks, venue info, etc. And if we focus in, for example, on these particular components, these are the set of components associated with the screens we can navigate to from the home screen shown here, corresponding to the tabs shown at the bottom: sessions, speakers, bookmarks, and venue. And a key thing here is that the components themselves know nothing about the UI. We just hook up particular UI elements to the, we just hook up particular UI screens to the appropriate component. Firstly, showing here the set of children defined for home component. And we'll explore here a little in the next few slides an example of how we'd navigate to the speaker's child and associated UI. So if we drill into a somewhat condensed version of home component, this is the Decompose component, which, as we mentioned, is associated with the home screen in our app. First important concept here is the child stack. It's described as a navigation model for managing a stack of components. The UI, as we'll see shortly, will observe the current active child in the stack and use that to decide what to show. The child stack is also passed a factory that's used to create child components, which we'll show next. This is the child factory mentioned, and it's used, as the name suggests, to create particular children given configuration passed to it. For example, config.speakers maps to child.speakers, which in turn is used to wrap an instance of speakers component. We also see example of how we navigate to that child in the onSpeaker tab clicked method that's invoked from the UI. That navigation.bring to front is passed in the config.speakers configuration, which, as we saw, will map to child.speakers, which then becomes the active child. This is how, in this example, we decide when to show that speakers UI, in this case, in the Android Compose client. We observe the active child instance from the component stack we saw earlier, see that it's set to child.speakers, as we saw in the previous slide, and then navigate to that screen, passing in, importantly, the associated child component as well, which in this case is the speakers component. An almost identical code in the iOS SwiftUI client, for example, again observing the component stack to decide which view to show. Next up is Multiplatform Settings library, designed to allow persisting key value data in KMP projects. So this is an excerpt from the Confetti project, where we're storing the name of the conference a user selected. If that value is set, then we bypass the conference list screen then when the app is, next time the app is launched. And we're also observing that setting as a Kotlin flow. That flow setting type of the settings parameter is an abstraction from the Multiplatform Settings library. And again, we use platform-specific code then to create the appropriate implementation of that. These are parts of the Koin platform-specific definitions for Android and iOS, for example, using DataStore settings as the implementation on Android, and NSUser default settings on iOS. The last library I'm going to show in this sample is Coil, one that folks might be familiar with from Android. It provides image loading, rendering functionality, and also now supports Compose multi-platform. And this is a small example of it being used to show profile image in the session details screen in Confetti. In this case, in shared Compose multi-platform code, that's also being consumed in the iOS client as shown here, which is partly why it's perhaps appropriate to use photo of Seb as an example. Next KMP sample is BikeShare. And this shows a list of BikeShare networks for particular countries and bike availability for each network. Again, we have Android and iOS clients, also a Compose for desktop client, and as shown here, a WASM-based Compose for Web 1. In this case, we're using KMP Observable ViewModel library for our shared view models, using Ktor to retrieve the data from the back end, and then persisting it locally using the Realm Kotlin library. And we'll be talking in this section about Realm, KMP Observable ViewModel, and also a plugin for generating Swift packages from shared KMP code. First library we want to talk about here is Realm Kotlin. As described in the documentation, it makes persisting, querying, and syncing data as simple as working with objects in your data model. So quite different from approach of, say, SQLDelight in that it supports working with objects directly, as we'll see next. OK, first thing we need to do is create a Realm instance, and we'll use that to interact with the database. We pass it the object types we're going to be working with, in this case, just one representing a bike network. And this is that bike network class, used, for example, for displaying the information shown on the screen, this screen on various platforms. And by subclassing a Realm object like this, we're able to directly persist the object to the database. And here's an example of code to iterate over the list of networks we got from the backend and write them to the database, using realm.write to create a transaction, and then copy to Realm to actually persist the object as shown here. An example of code then to read those network objects from the database, returning a flow, which again we can use to drive our UI. Next up is KMP Observable ViewModel. This is a library that up to a few weeks ago was known as KMM-ViewModel. It's now described as a library to use Android X Kotlin view models with Swift UI. And a key aspect of what this offers is the ability to expose Kotlin state flows, for example, as Swift properties that can be directly observed in Swift UI, as we'll see shortly. And this is an example of the shared view models in the BikeShare project. In this case, exposing the list of countries we're displaying. We're using our repository class to get the list of countries, doing some transformation of that information, and exposing then as a state flow. And this is how that's consumed in SwiftUI in the iOS client. We instantiate the view model we saw in the previous slide, using the @StateViewModel property wrapper provided by the KMP Observable ViewModel library, which then allows that country list state flow from the ViewModel to be observed directly here as a Swift property. And this is the Android Compose equivalent. On Android, we observe the state flow as normal, using, for example, collect_state, as shown here. And as with Swift UI, any change to the country list will cause the UI to be recomposed. Next up is a Gradle plugin that generates a Swift package from your shared code, which then can be easily consumed in Xcode. This is an example of the associated build config for the BikeShare project. Here we're targeting the iOS and macOS platforms. In this case, the output of the plugin is published to a separate GitHub repository, but could also be done in the same repo. That repo, by the way, includes example of Swift UI code you can use then to consume the Swift package, as we'll see next. And a small recording then of showing how to add that Swift package to an iOS project in Xcode. We start with a new iOS app project. We then copy the URL of the GitHub repository containing the package and use that to add a package in Xcode. Lastly, we copy the example Swift UI code from the repo and paste that in, and we're ready to go. Wanted here also to show just how easy it is in general to consume a Swift package containing shared KMP code like this. And what's shown here is the same regardless of how that package is created. And we see here the super basic iOS app showing the list of bike stations for a particular network, built from consuming that Swift package. And by the way, another more recent and much more comprehensive approach you can use for creating such packages is KMMBridge, which I definitely recommend people looking at. It takes care of both producing the package and publishing it, and also provides capabilities for local development. It's an approach I've actually started to explore using in the Confetti project. Okay, the second last sample we're going to use today is Climate Trace. This shows per sector emission information for different countries. Again, we have an iOS and Android client, and also a Compose for desktop client and a WASM-based Compose for web one, as shown here. In this project, we're using the KMP Observable ViewModel library again to share our view models, Ktor to connect to the backend, and Ktor to persist the data locally. And this sample is also using shared Compose UI code across the clients. Here we'll be talking about Voyager, window size class, Compose on iOS, and Jetpack navigation. So first up is Voyager. This is primarily a navigation library that works across a range of Compose multi-platform clients. It supports a wide range of functionality, including different navigation types, state restoration, transitions, lifecycle callbacks, backpress handling, and deep link support, along with integration with a number of other frameworks. It works on the basis of having your Compose code contained in these screen classes. This is an example from Climate Trace of the screen showing the list of countries. We see then use of Voyager's navigator.push when an entry is selected in that country list, causing us to navigate to country emission screen, passing in the country object. And here is this excerpt from country emission screen. You can see here then use of Voyager's navigator.pop to navigate back to the previous screen. Another Compose multi-platform library we're using is this port of Android's Material 3 window size class library. This allows creating adaptive UIs based on a set of Windows size breakpoints that we can generally apply across the various clients. And in this example of different layouts, we dynamically show depending on the screen size, showing list and detail in a column on the left, and then showing in a row as the window is resized. And we see this in action as well here. These particular layout configurations are, of course, just one example. Another common approach is to switch between list detail and list as the window gets smaller. And this is the still version of some of the code used. The specific layouts here aren't too important. Key thing here is how we're querying for the window size class in common code, showing different layouts depending on what it's set to. And the UI will get recomposed then whenever a change causes the width or height of the window to cross a breakpoint. Next thing I'm going to show here, also from Climate Trace project, is a small example of shared Compose UI code being consumed on iOS. We have, for example, this function exposed from our iOS main code in our shared KMP module. It uses Compose Multiplatform's Compose UI view controller, which in turn includes the country list view composable. That composable is in shared KMP code and used in Android client as well. And then on iOS, we take advantage of the ability to include a view controller in SwiftUI code. Here we define such a view controller, this country list view shared struct. And that in turn invokes the shared Compose country list view controller we showed from the previous slide. Here we also pass a callback that's invoked when a country is selected in the list. And this is an approach I'm using in several of the samples. Lastly, for this sample, Jetpack navigation. We're going to use experimental version of the library that was included in a recent Compose Multiplatform beta and expanded on in subsequent versions. This shows some changes that were added to the Climate Trace project to try it out, available in a branch if people are interested in taking a look. Same code as we'd use, for example, in an Android app, but this is shared Kotlin Multiplatform code. We define a number of routes which we can navigate to. For example, the list of countries and details for a particular country. This is a nice capability to have now, and one more thing that will make migration from existing Android only apps much easier. And we'll talk a bit more about the various other Jetpack libraries that now support KMP in the next section. Next up is Fantasy Premier League, the last of the KMP samples we're covering today. The project displays information for a competition for the main football league in England. There are screenshots for the Android and iOS client. And this is the Compose for desktop client as well. So in this project, we're retrieving the data from the backend using Ktor and storing locally using Jetpack Room, thanks to its new KMP support. We're also using shared view models, but in this case, we're using the recently announced version of the Jetpack ViewModel library that also now supports KMP, and using shared Compose UI code here as well. In this case, for the player details screen we'll see shortly. And in this section, we're going to talk a little about the use of aforementioned Jetpack ViewModel, Jetpack Room, Jetpack DataStore, SKIE, and KoalaPlot libraries. So as you've probably gathered, this project has sort of become my designated Jetpack KMP sample. As you can see here, we rapidly got to a point where several key Jetpack libraries are now available to be used in shared Kotlin multiplatform code. I think this is something that has really excited the developer community. Now, whether or not these libraries are the best solution for a particular functionality they provide is a different story, given the options we now have in the KMP world. But the key thing is having them provides a very nice migration path for existing Android apps. One library I forgot to include in that list at the time was Jetpack Paging, which actually had its first stable release just last week. And this is used, by the way, in the Morty KMP sample, one of the other KMP samples I have. And speaking of Jetpack libraries that's supporting KMP, this is a topic that some folks from Google will be talking about later today. So really looking forward to that. So first of these Jetpack libraries is ViewModel, one that would probably be very familiar to Android devs out there. Used as part of a general MVVM pattern, its role is primarily as a container or holder of observable UI state, and as a conduit of actions that would typically affect that state. The Jetpack version has had some additional responsibilities in the Android world around the caching of state through configuration changes and as part of navigation graph, etc. With the KMP support now, and importantly also that of the lifecycle library, this has been generalized to work on other platforms as well. So this is a small example from the project. Looks like a standard Android view model that many of us have used in Android before. Difference here is that this is defined in shared common Kotlin multiplatform code. We'll talk shortly, by the way, about how we're using the SKIE library to access that state flow in SwiftUI code. An example then of using a recent Coin update that allows injecting such a view model into shared Compose UI code. Next library we're going to talk about is Jetpack Room. It provides, as described here, an abstraction layer over SQLDelight. And this is one of the entities from the project that we're going to persist, in this case for information about a particular player. Just a standard Kotlin data class marked with @entity annotation. We then have this abstract class in common code representing the database. that's also used to access our data access object. We're also providing here the list of entities we're working with. A SQLDelight database table will be created for each of those. And as we've done elsewhere, we use KMP's expect actual mechanism to create the platform-specific implementation of that app database class. And this is the database access object we referred to in the previous slide. Here we define various database queries we'll be making, showing just the ones related to a player here. We have methods for inserting the list of players, returning the players in the DB as a Kotlin flow, and then retrieving a particular player by ID. It's this class we'll be using in our repository. And showing excerpt from that repository class here, we inject the app database instance, again using Coin, and then use it to get the data access object, which we use then to write the info to the database, and also expose what's in the player table in the database as a flow, along with a method to get particular player by ID. Similar to ViewModel, DataStore is yet another Jetpack library that now supports KMP. It's been available in pre-release versions for a while, but went stable recently. It supports storing key value information, as well as typed objects using protocol buffers. This sample had, in fact, been using the Multiplatform Settings library that we saw earlier, but it was recently migrated to use DataStore directly. And this is an example of it being used to store the particular fantasy league a user is part of. The DataStore object is injected into the constructor, again by Coin, with implementation again being created in platform-specific modules. We have methods to update the list of leagues, and also return the list of the list as a flow, which can be observed. And this is what we have in the platform module for Android. The specific details aren't too important, but just to show again how KMP's expect actual mechanism, in conjunction with Coin, allows us to easily plug in platform-specific code like this. And then this is for iOS. Again, we won't focus too much on the specific implementation here, details of how that data store is created, but again, the same mechanism used. Next library we're going to talk about from this project is SKIE from TouchLab. SKIE stands for Swift Kotlin Interop Enhancer. And supports a range of functionality as mentioned here. We'll show next how we're using some of these features in this project, specifically the coroutines flow and seals class support. First up, invoking Kotlin suspend functions from Swift. We have this get event status suspend function in shared code. And we're able to use Swift's await to invoke it then in our iOS client, thanks to SKIE. And likewise for flows. We have that player list UI state flow in our ViewModel, and they can then use Swift's for await to observe that in the iOS client. That Swift for await, as mentioned before, is analogous to Kotlin's collect. And as with KMP Native Cortines, when the Swift UI screen that's used in is no longer shown, then this is cancelled, and that cancellation is propagated to the Kotlin flow as well. Another area where there's somewhat of a disconnect between Kotlin and Swift is seal classes, and this is something SKIE also addresses. We have this player list UI state seal class that's being emitted from our ViewModel, as we saw before. SKIE then provides a way to exhaustively switch over the sealed class hierarchy by generating a Swift enum that wraps the Kotlin sealed class. And we can see an example here in Xcode where it reports the switch must be exhaustive error then if any of the cases are missing. I mentioned we were sharing Compose UI code for the player details screen across the clients. That screen shows a graph, and we're using the KoalaPlot CMP library to show that. It supports a wide range of different chart types, but we're using it in this project for a standard bar chart, as we'll see next. And this is a somewhat condensed version of the code then to show that chart. Key thing again is that this is shared Compose UI multi-platform code that we use for all the clients. For example, in the iOS client shown here. So that was a whirlwind tour of many of the Kotlin and Compose multi-platform libraries used in various KMP samples I'm involved in. Showing here again the ones we covered today, broken down by function. We have libraries, for example, for persistence, remote API requests, dependency injection, ViewModel component sharing, navigation, Swift Kotlin interop, packaging, and then some Compose multi-platform UI libraries as well. Hopefully you got at least a flavor of these capabilities that these libraries provide, and how they can be used. As mentioned, I'll make the slides available so they can hopefully act as somewhat of a reference for the material we covered here today. Thank you.